So yesterday's lecture was about radioactivity, and radioactivity has a lot to do with today's topic, which happens to be something that we call half-life. So just a little couple of things to review before we move forward. One of the things that we talked about yesterday was that there were types of particles associated with radioactive decay. And there were three particles that you were responsible for understanding. The first one is the alpha particle, and the particle that is produced is called the alpha particle. But remember, that's a helium nucleus. Right? So it's the helium. Okay, so that was not the first, but that was definitely one of the ones that we discussed yesterday. The second one that we discussed yesterday was beta, and the particle as produced is a high energy electron. Okay, so that's a high energy electron that is emitted or released from the atom, the unstable atom, and then the gamma was a produced light particles that we called photons. So that's a little review from yesterday. The second thing is that that we did yesterday is we actually learned about what to do in this situation here. So we had carbon-14 undergoing beta decay. And in beta decay, an electron, so what we have to remember is that in beta decay, one neutron changes or splits into one proton and one electron. So in this example, because it's beta decay, I know that I have an electron being produced. I also know that I have one proton being produced, which means that my atomic number here is going to increase by 1, so that's going to become 7. The mass number is going to stay the same. So that's going to be 14. And so that's going to tell me that my element is, now I'm going to locate element number 7 on the periodic table, and that's going to be nitrogen. Okay. Now, radioactivity is the new term for today. So radioactivity is defined as the emission which means to give off or release, the emission of ionizing radiation as an atom's nucleus breaks down and or decays. Radioactivity is harmful to humans, depending though on the type of decay. And so I know that some of you are kind of wondering, which type of decay would be harmful. Well, we talked a little bit yesterday, and we said that all radiation is there are limits that you can absorb, but some is worse than others. So we talked the fact that non-ionizing radiation is less harmful than ionizing radiation. And that's just something that we have to keep track of or think. So how do we detect radioactivity and or radiation? Well, scientists will use a tool that's called a Geiger counter. And they use that Geiger counter to detect radiation. So I'd like you to take a second or two to think about what around you or common sources of radiation or radioactivity. So what common sources do you expect to be radioactive? And especially, specifically, give off ionizing radiation. Now, I'm not going to answer that specifically here, but I want you to think about it and where you might see it. So I will be showing that in class during the hour. What I'd like you to do now is pause this video and go ahead and watch it. It's about 3.5, 4 minutes long, and then come back. But there is a video that I'm going to show in class that is about detecting radioactivity. So after you've watched the video, hopefully you have a good idea of things that are radioactive and what it means to absorb radiation and how that can have an effect on a human being. But to go a little bit further, we need to talk about protection from radioactivity. So alpha radiation is the least penetrating of the three types of radiation that you're going to be responsible for understanding. And you can see that by looking at this diagram down below. Alpha radiation will stop with your hand. It will also stop if I hold a piece of paper in front of it. But beta radiation will go through a person's hand or a piece of paper, but it will stop by it will be stopped by a metal, like in this case aluminum. So if alpha radiation is the least penetrating, that would make then gamma radiation is the most penetrating. So gamma radiation will go through a human's hand, it will go through a piece of paper, it will also go through aluminum, but when it gets to a really dense metal like lead, it will stop. So gamma radiation, because it is the most penetrating out of the three that you're responsible for understanding, is potentially the most, has the most hazard to humans. Okay, so half-life. That's the point of today's lecture. So some things to think about. So about half-life as a sample of an element, radioactively decays less and less of the sample remain. over time. This is called the half-life. So the half-life of an element is defined as the amount of time it takes for half of the sample to decay. Work through a couple of examples and how to work through those things and figure it out. So, first things first. We're going to use a fictitious element. This is the element zirconium, named after the great physical science teacher, Miss Cisco, from Greendale High School. So the half-life of zirconium is 3 days. So what I'm telling you is that after 3 days, half of what you start with will be left. So I'm telling you that in the original size of your sample, in this case, is 80 atoms. And the question is, how many atoms will remain after one half-life, which in this case is 3 days? Well, half, I would simply take 80 divided by 2 to get 40 atoms. So that's one half-life. And if I wanted to go and find out what would happen after 60 days, I would take 40 divided by 2, and that would get me 20 atoms. So that's 2 half-lives. And then after 9 days, I would take 20 divided by 2, because that's half, right? And that would give me 10 atoms. And that would occur after 3 half-lives. And then lastly, after 12 days, I would take 10 divided by 2, which would give me 5 atoms. And that's would be 4 half-lives. So after 4 half-lives, I'd be left with simply 5 atoms. And we could go further, and eventually we get down to nothing. But this is kind of what you need to understand. Now, sometimes you're going to be looking at an example or a problem where you're told how much you have, and you need to figure out how much you started with or was started. So in this problem, I'm telling you that after 4 years, there are 2 grams of lashmium, another great physical science teacher from Greendale High School, left in your sample. If the half-life of lashmium is 1 year, how many grams were originally in the sample? So after 4 years, I'm starting with 2 grams. Okay? The question is asking me to determine the original size. So remember that every half-life, I cut something in half. So if I want to figure out how much I started with, I need to go back and multiply things by 2. So I'm going to take 2 times 2 to get 4. So after 3 years, I have 4 grams of lashmium. And after 2 years, so I'm going to do that again. So this time I'm going to take 4 times 2, which will get me 8. So that after 2 years, I had 8 grams of lashmium. And then I'm going to do the same thing to figure out after 1 year. So I'm going to take 8 times 2, which is 16. So I have 16 grams of lashmium. And then if I'm going to go back to my original size, I'm going to take 16 times 2, which is 32. So now I know the answer is, in this case, 32 grams. grams of lashmium. So how many half-lives had occurred? Well, it appears that we had 1 half-life, 2 half-lives, 3 half-lives, 4 half-lives. So there were 4 half-lives that had occurred to get to 2 grams. And we were able to work backwards by multiplying to determine what the original size was. Okay, so that's all I really have for you today. Your homework is to go and do the half-life worksheet number 3. It is a 2-sider, so good luck with that, and we will talk about the answers to that next time.